For this, I would like to introduce Irene Patric. Irene holds a master's in biotechnology and has more than 10 years of experience working as a scientist in the field of clinical genetics and medical bioinformatics. And since 2021, she's with Limbus, where she serves as a product manager and clinical applications specialist. And today she will talk about automated shortlisting of variants powered by inheritance filters.
Thank you, Yvonne. And yeah, I'm happy to talk about the inheritance filters, how they normally work, and how at varvis we work towards improving these, and why the technical details are important. And so yes, thank you for asking this question already on how long this takes to complete a case on average. So it can range anywhere from 15 minutes to a couple of hours. And there's really, like Robin already said, depends on the case, but also on the workflow that has been set. It differs from laboratory to laboratory, but also largely on the tool that is used for analysis. And at varvis, thanks to Robin for also explaining how a set workflow helps in accelerating the process, right? And with varvis, you're able to do this in two ways. One is each person is responsible for their own work. You set up your own workflow, and then you pass it to another person, and they have their own workflow with which they are able to test it. But now another way is that you have a SOP, and the whole laboratory agrees on a single workflow. You set it up, and every user can add their own steps to this and do the analysis the way they want. But a large portion of this, I would say, is also the inheritance filters, especially in large familial cases. And for these, it's much beyond just segregating heterozygous, homozygous, and just saying, okay, these are the filters. But there are several technical details that need to be taken into account. So I will be talking a little bit on this. So for familial cases, there are several things that need to be considered. And are all tools same when it comes to inheritance filters? Because there could be inclusions, there could be exclusions based on these factors that are considered. And the right balance is important so that no important variant is missed out. So what are the common solutions we see across tools? One is, of course, you need to check whether the individuals are affected or unaffected. And then you have the zygosity that you must take into account. And yeah, sometimes people also filter in addition for mode of inheritance, but a better way is segregation. But several tools also, how do you say, they cannot go beyond duos and trios. So the pitfalls are that several tools are unable to do the segregation for large families. And then there is a huge topic of mosaicism. And yeah, this itself is a whole big topic. And hopefully the next time we'll be able to shed more light on this. But I will be touching on this. And then there is pseudo-autosomal regions, where these are regions in the X and Y that follow the autosomal pattern of inheritance and not the regular sex chromosome pattern. And then there is CNV as second hit also. So I will be explaining how all these come together for inheritance filters. Now, when it comes to categories of mutations, we are quite aware of the inherited mutation autosomal dominant mode, where an affected parent passes on the inherited, transmits it to the child. And then there is, of course, de novo. So autosomal dominant many times combines these two. So I will start explaining how filters are built. And this is the most simple filter you will find, that you, for an affected individual, should be heterozygous, and unaffected family members should not carry the variant. Now, to add a layer to this, when it comes to X-linked de novo, then we have to separate the genders. So the male would be hemizygous and the female heterozygous. Simple. Now, adding a layer to this, pseudo-autosomal regions. Now, this is going to have a different zygosity. So what happens is, when you're considering the PAR, you have to then say, okay, in a regular scenario, yes, males will be hemizygous, but not so with PAR, revert it to heterozygous. So you're adding layers on layers for inheritance models, and this is how our inheritance filters are built. So when it comes to a normal solution, you would see that several times these are combined. And then manual work would be required to see who is affected, who carries what in what zygosity. So after applying all the default filters, then there is some manual work involved, which we are trying to overcome and make it easy for the user so that in one click, you have only the most important phenotypic overlap and so on to take care of. And also, varvis considers pseudo-autosomal regions as a separate one. Now, in addition, like I said, is mosaicism, which is a big topic. But I will just touch upon Mendelian presentation of this, where a parent is a carrier, but is not affected themselves and passes on to the child. Now, again, I will start off with the autosomal dominant filter, a simple inheritance. But when it comes to this, when you have an additional affected family member, so you would like to see this in the tool on one click. Of course, there are certain tools that cover this as de novo, but is it really de novo, and how much effort you have to put into checking, cross-checking, cross-verifying this information, this is also there. So I will also later in an example show how when it comes together in one click, why it makes it much easier. We are still missing something when it comes to de novo, which is de novo homozygous variants. So I will say why here. So several tools work like this, where an affected individual is homozygous and the parents must be heterozygous each. But would this scenario be covered by the filter when one of the parent is only mosaic and not really detected by WES? Or this could also be the scenario like in the paper where homozygous de novo variants were detected. Now, the mechanism underlying could be different, but in spite of that, we have seen this reported in some cases, and it's important that these are being detected. So when it comes to common solutions, you see that they're restricted to trios, but varvis considers affection status and zygosity of all family members involved, and different relationships are considered, including aunts, uncles, and grandparents, and it doesn't matter, and large families can be analyzed at once. And we also consider a de novo variant for second hit. So the most complex filter, of course, is compound heterozygous that was quite difficult to build upon because it has several layers. Now, this is how a regular filter will be built. Compound heterozygous in the affected individuals and the parents must be heterozygous for one variant each. But when it comes to mosaicism, and if one of the parents were carriers, so this is how you would see that you would have a compound heterozygous situation, but you wouldn't see it in one of the parents. So if your filtering tool is very strict with these, then you may miss out such variants, and the diagnosis, of course, then would be affected. The second layer to this is, of course, the second hit being CNV. And in many tools, you would have to switch between the views, or you would really have to go hunting for the second variant. But when it comes together, of course, diagnosis is made much easier. And when it comes to X-linked, then there's more than this. You have the sex differentiation and then the pseudo-autosomal region that also needs to be considered in addition to this. So we consider de novo variants for CHDN and also the pseudo-autosomal region. And of course, considering CNV as a second hit is very important, and I'm sure all those who have analyzed have always seen such cases. Yeah, so with our team, with Christian and Lena, we have worked on these inheritance filters, 7, and including the carrier screening filter, it's 8 filters in total, and we have tested it quite largely, and yeah, 140 distinct test scenarios. We verified this in every software update. We have a high level of transparency with our users, with very convenient training material. And to just say, this is an example of how it would look in our user manual. We explain to the users what is being filtered in for every click and what is removed. And the logic behind the filter is also made very transparent to the user so that they understand what is being shown and how it would help with diagnosis. So this is an example. Of course, everybody would like to see how it looks in varvis when it all comes together. So I put together this example. This is an X-linked recessive disorder where the index is female and has SNV and a CNV. And of course, the brother is also affected and has inherited the CNV from the unaffected mother. Of course, then this SNV looks like a de novo variant. Not so much when there is an additional affected sister. So you then can understand that there is a possible mosaicism scenario involved. And so if I have to ask, what if a second hit de novo is not considered, for example? If the filter was very strict and we excluded this variant because you don't see the segregation that you expect. So that is one question. And the second question would be, what if the CNV information was not there? Then you start digging, and is this really an X-linked recessive disorder? What is, or do I have to look for another variant? Have we missed another variant while sequencing? Is there a CNV? You go to the CNV view. So there's a lot of digging that is required, and this is made much easier for our users with varvis. So in summary, I'd like to say, yeah, choose the analysis tool with caution, and because scientific design and automation are very important, and validation testing of the pipeline is essential. It's crucial. And with varvis, we help the users with validation of the entire pipeline. We are able to give feedback. We help with testing. So this is very important. Of course, then there are several people who say, are all these inclusions extremely important? I would say there are not many tools that help with this, bringing together the things, and then diagnostics becomes more difficult because you're always looking for something in addition. So yes, I'm very happy to say that we are continuously working on improving things and always in discussion with users. So yes, thank you very much for your attention, and see you next time with more interesting features. I'm open to questions.
Thank you, Irene.